Hi, I'm Dr. Califf, and today I'd like to talk about normalizing data or feature scaling in machine learning. Suppose we have some data with three features. The first one has range 1 to 300, the second range 1 to 5, and the third range 1 to 60. Question for you, does the range variation here actually matter? As in most things in life, as well as machine learning, the real answer is it depends. So let's think about a decision tree. With a decision tree, we usually would not need to normalize our data. Each feature is considered individually in the process. So in the decision tree, we're going to look at feature 1, perhaps, and make a decision about that value. Then after we have that answer, we'll take a look at feature 2. We're not going to have the features interacting with each other. So the fact that one has a larger range than the other doesn't end up mattering. In fact, in decision trees, we don't even have to have numeric features at all. We can look at color, for example, and divide by these things are blue, these things are red, these things are green, without having to ever worry about what values we're using to represent those categories. On the other hand, with the neural network, normalization is really important in general. Our features are actually interacting mathematically. So let's take a look at a very simplified piece of a neural network. I have input of the 3 different feature values. Each of those is connected by a weight to a node. And the output of that node they're connected to is going to be the value for feature 1 times the first weight, the value of feature 2 times the second weight, plus the value of feature 3 times the third weight. And then we're going to pass that sum to an activation function. You can imagine that figuring out what those weights should be when one of these values can go up to 300 and the other one has a maximum value of 5 could be challenging, to say the least. Let's actually take a look at the behavior of these two learning models with and without normalization. So here we are in the code we're going to use to take a look at this feature scaling concept in neural networks versus decision trees. If you watch my overfitting video, this is going to look somewhat familiar. We're using scikit-learn again, and we're going to use the breast cancer data set again. So we're going to take our data, and we're going to produce 2 scaled versions of the data. First of all, one that uses the standard scaler that's built in, and the other that uses the min-max scaler that's also built in. We'll talk a bit about the difference of those in a minute after we look at our example. We'll look at the neural network trials unscaled. So we're going to use a hidden layer size of 16, which is a pretty reasonable size for this data set. We are going to run 5 trials with the neural networks because there is some randomness built in there. It's important to run multiple trials to get a sense of what's really going on with neural networks. We're going to get the training, do the training and predictions with the unscaled data. Do the same thing with the scaled data. And then with the scaled data using the min-max data. So we've trained with each of those, done the fit with each different kind of data, and done the predictions on similarly scaled test data and trained data both. Then we're going to just take a look at what some of the data looks like so we get a sense of whether there were different scales in this particular data set before we scaled it and what it looks like after it's scaled. Then I want to take a look at the impact on decision trees. So we'll do the same kind of thing. We're not going to do multiple trials here because decision tree learning is much more deterministic, doesn't have the randomness to it that the neural networks do. We'll see how it behaves with the unscaled data and with the 2 different kinds of scaled data that we're looking at. Let's go take a look at the actual results we got. Here we are in the results of the trial. We've run the file we were just taking a look at. For our unscaled neural network trials, we're seeing 78%, which feels very low, particularly if you happen to watch the overfitting video. This one is not the results that we're used to seeing, and that's because we scaled the data. If you take a look at that code in that video, we scaled the data there. So that's how we got good results. However, if we scale the data here, again, we get good results, 99% on train, 96.6% test accuracy. The min-max scaling does even better, only 98.9 on train, but 96.9 on test accuracy. So we can see that the scaling made a huge difference. And let's take a quick look at why here. So if we just cherry pick some numbers with 483 actually, versus 0.007. So large differences in value sizes of these features in this data set. We see a 0.009 here. There's one, here, we've got over 1,000 in this one, and other values that are 0.004. So we see the values hugely different. If we look at our standard scaled data, we're going to see values generally between -1 and 1, though that's actually the standard deviation. So you'll see some things that are a bit higher because they're more than one standard deviation outside the data. But as you can see, I don't see anything in this data that's above a 2. So all fairly close to that 0. With the min-max data, we're going to actually see everything between 0 and 1. Within the training data, every single thing will be between 0 and 1. And this is why we get this improvement. Because of the mathematical interactions, we get much better results. The weights are able to handle the variation in the data much better. Now let's look at the decision tree results. With the unscaled data, we see that we're doing much, much better than the neural network does on unscaled data. Nearly 92% accuracy on test. Now notice that once we have scaled the data, we're actually doing the same. So the neural network is able to do a much better job with this data set once we scale the data for it. So there are two main types of scaling that we use, the two that we experimented with. Min-max scaling is to scale to fit in a specified range. So we just say, okay, I want my data to go from this low point to this high point, usually 0 and 1, and I'm going to make it all fit within that. Z-score scaling, or standard scaling, is scaling so that the mean is 0 and the standard deviation is 1, which is why we were seeing some values sort of outside of that -1 to 1 range. There are other approaches that are a little more complex. If you're interested, I recommend taking a look at robust scaling or logarithmic scaling. I want to quickly look at the math for these two, min-max and the standard scaling, just to give you an idea of what this looks like, and that it's fairly straightforward, although you should never have to do it because machine learning libraries typically have these capabilities. As you saw, we were using the ones from scikit-learn. So first of all, for min-max, we're going to just go through the training data. We're not going to touch our validation or test data. We want to keep those separate from the whole training process, including this part. We're going to find the minimum value and the maximum value. Then we're going to pick a min and max, typically 0 for the minimum, 1 for the maximum. Math gets a little bit more complicated if that's not what you choose. For 0 and 1, the formula is going to be the scaled value. It's going to be the value minus the minimum value of the data. Then we're going to divide the result by the range. So the max value minus the minimum value is the total original range of values. So that'll get us down to a number between 0 and 1. Standardization, or the Z-scaling, we're using the standard deviation. So that means we've got to go through the training data, find the mean, and then compute the standard deviation of the feature. Now, I'm not going to go into that there. Recommend checking out a good math resource if you don't know how to compute standard deviation. Once we have those values, the formula is going to be the scaled value is the value minus the mean, because we're working around the mean, divided by the standard deviation, because we want our new standard deviation to be 1. So if we divide by the original standard deviation, if we're within 1 standard deviation, we'll be between -1 and 1. Otherwise, will be the next value out based on how many standard deviations this value is out from the original. So this gives you an idea of how these things are computed for the basic types of scaling. Again, they're in libraries. You should never have to compute them unless you want to. When do we normalize? When do we need to scale our features? The biggest thing is if our features are interacting mathematically, and I have features that have very different scales, or even just different scales. Want everything to be in the same basic scale. Neural networks, heavily mathematically interacting between features, we saw how dramatically our results on that data set improved when we scaled the data. Distance-based techniques, so things like nearest neighbor or clustering, those, because they are computing distances, if one of the features is very large range and one is very small, the large range feature is going to have a much greater impact that is not necessarily appropriate. So we want to get everything normalized. Support vector machines, or SVM, also are using this kind of mathematical interaction. And then regression, any kind of regression, whether linear, nonlinear, logistic. Again, we're doing math with the feature values together. We need for them to be in similar ranges for it to work well, especially for it to easily work well. There are also algorithms where we don't need it, may not want it. It might actually hurt our results in some cases. So tree-based algorithms. Naive Bayes. So in naive Bayes, we're dealing with the probability of each feature separately. We've turned these into probabilities by the time they're interacting. So we've handled the problems with the math before we get to that point. Rule learners. Things like Ripper, if you've heard of inductive logic programming, these things don't need it, don't want it. And most rank order models are also not needing to be scaled. Notice that for many of these models, these are producing models that are understandable by humans. So it's not desirable to change the ranges of values just because if you change the income or age or amount of debt or GPA, whatever it might be that you're trying to learn from, if you change these values to be in some sort of normalized 0 to 1 or -1 to 1 kind of a range, it's going to be very confusing for the human trying to understand your model. One of the big advantages of some of these models is that they are very human understandable, so we don't want to throw away that understanding with scaling. Thanks for watching. I hope you got something out of this, understand a little bit better what feature scaling or data normalization is in machine learning and why and when we would want to use it. If you got something out of it, I'd appreciate a subscribe, a like, a comment. Always glad to answer questions if anything here was confusing. Hope to see you next time.